Today's lesson is a brief introduction to exponents. First, we want to know what each part means and what it's called. So here's an exponent. You've seen exponents before, and it's the number in the top right of a bigger number. Now that bigger number is the base, and the number on the top right is the exponent. Now, a common mistake here is that students often want to do 2 times 5 to get 10, but that exponent is never a number that's supposed to be multiplied. It just tells you how many times the base is being multiplied by itself. Now, there are 7 exponent rules that you need to know. I suggest that you write these down in your notebook for you to reference later. Now, the first one, anything raised to the 0 power is always going to be 1 except for 0. So if I said 10 raised to the 0 power, that's 1. If I said -3, all of this has to be raised to the 0 power. That is also going to be 1. If I said 1 million raised to the 0 power, that's 1. If I said x to the 0 power, that's also 1. I could say anything really raised to the 0 power except for 0, and you would get 1. The second rule, the very important thing here, and really with the rest of all of our rules, is that you have to have the same base. So here we have an A and an A, and our exponents are different. One's an M and one's an N, and as long as they're the same base, then you can do this rule. Now, an example, and when you multiply and you have the same base, you're actually going to add those exponents together. So I could have x to the 2nd power and multiply that to x to the 3rd power. We are not going to do 2 times 3. We are going to make this x to the 5th power. Now again, this is only possible because we had the same base, and you keep that base with your response. I could have a to the 10th power times a to the 3rd power, and I'm going to get a to the 30 power. You don't have to have just a variable as the base. You could say 2 to the 10th power times 2 to the 5th power. And let's say you don't want to multiply each of these out separately and then multiply them together. You would just add those exponents together to simplify it. You could have x plus 1 to the 5th power times x plus 1 to the 6th power. And I'm making these more complicated on purpose so that you can see, even when we change our base to be something that looks super complicated, we are still going to keep the same base. You just add those exponents together. Okay, the next rule. Now, if we're dividing, our previous one was if we're multiplying. If we are dividing, again, we're always going to have to keep that same base. So this is not going to be true of those a's that were different from each other, but because they're the same, we can subtract our exponents together. So I could have x to the 5th power divided by x to the 3rd, and that's going to give me x to the 2nd power. I could have 3 to the 5th power divided by 3, and any number without an exponent would be to the 1st power. So if it just said divided by 3, then you would assume an automatic exponent of 1, and we would subtract that 5 minus 1 to give us 3 to the 4th power. A question might cross your mind, well, what if the numerator exponent, let's say it's a to the 7th power, what if that's smaller than your denominator? You're still going to subtract those from each other. We're still going to say a to the 7, minus 10. And we can get a negative exponent. You're going to learn in a future rule what happens when you have a negative exponent, but it's okay if that happens. So again, if I had 3 divided by 3 to the 5th power, which is what this previous one was, I just made it become the reciprocal. If it doesn't have an exponent, it assumes an automatic exponent of 1. We're still going to subtract our exponents from each other, and it's going to get a 3 to the negative 4th power, and that's okay. Exponent rule 4. This is when you have an exponent raised to an exponent. You don't have to worry about having the same base here, and that's because there's just one base to really assess, and you just keep that same base. So let's say you had x to the 5th power raised to the 2nd power. That's when you're going to multiply them together to get x to the 10th power. You could have 5 to the 3rd power raised to the 3rd power. Keep that same base, and it's now to the 9th power. You could have z to the negative 4th power and raise it to the 2nd power. Well, negative times a positive makes a negative, so it turns into z to the negative 8th power. Don't be scared of those negative exponents. We're going to learn what to do with them in just a moment. Exponent rule 5, this is still very similar from our previous exponent rule. The only difference is what if you have 2 things inside of your parentheses. So here, these are not the same base. They are different bases. They both are considered a base. The only thing that happens here is that exponent, that x, goes to both of them. So if I had, it has to be in parentheses so that you know that they're lumped together. If they're not in parentheses, this exponent isn't going to go to both. But I have a 5 and an x inside the parentheses, so that 2nd power is actually going to go to both of these. I haven't been fully simplifying because I just want you to understand the rule. But if you know 5 squared off the top of your head, yes, you are allowed to go straight to 25x squared. It could be xy to the 3rd power, and you would get x to the 3rd, y to the 3rd. Here's when it starts to get a little tricky. If you have, let's see, 2x to the 2nd power raised to the 3rd, this is when you'll have to bring into play exponent rule number 4, where you have an exponent raised to an exponent. Now this 2 doesn't have an exponent there, so you're going to assume an automatic 1. And when you have an exponent raised to an exponent, it's going to multiply. Let me go ahead and separate these. This 3 is going to go to both of these, just like what we learned in our previous 2 examples. And then based on exponent rule 4, we are going to multiply this together. So 2 raised to the 1st power raised to the 3rd. 1 times 3 is 3 times 2 times 3 is 6. And if we wanted to continue simplifying, 2 to the 3rd power is 8. So it would be 8x to the 6th. I know I'm going fairly fast. You'll have some you-try problems at the end. And this is just a very brief introduction to exponents, just to get you started. Okay, exponent rule 6, the same thing is going to happen even if you are dividing. So if you have, let's see, x divided by y, all raised to the 3rd power, just like what happened in the previous rule, exponent rule 5, it's going to go to both parts. There's nothing left out here. If I had 5 over a to the second power, and this is all raised to the second power, then we're going to raise both our numerator and our denominator, but since that a already had an exponent, we're going to have to raise an exponent to an exponent. This is where we'll have to do a little bit more simplifying. 5 squared is 25, and 2 times 2 is to the 4th power. Okay, we have one more rule to address before you try some on your own. Last one. So we talked about negative exponents and what happens. And as you can see in this example, it looks like you just move it to the denominator. And if there's no numerator, then the numerator becomes a 1. Now, the reason why this numerator becomes a 1 is because there's already a 1 in your denominator. And so if we're going to move this to your denominator to make it positive, we need to keep a placeholder there. It can't be 0 or else the whole thing would turn 0. So we need to turn it into a 1. So if I had 5 to the negative second power, I have to move that to the denominator to make it positive, but I still need a numerator, so it's going to be 1. If I had 3x to the negative second power, that 3 is actually not negative. It's just the x that has the exponent that's negative. I don't know why I put this fraction bar because it wasn't a fraction, but it's going to turn into 3 is going to stay on that numerator because there's no exponent to the 3 that's negative. It's just the exponent to the x that is. And we're moving it to the denominator to make it positive. Now, every time you have a negative exponent, it doesn't mean it moves to the bottom. It does if it's on the numerator, but if you already have something on the denominator that's negative, so the negative 4th power, essentially we're just moving it to the opposite side of the fraction bar. So if it's on the denominator to start with and it's negative, in order to make it positive, you're going to move that up to the numerator to make it positive. So you're just switching what side of the fraction bar it is on. Okay, so now we're going to dive into some you-try problems. So the first one is going to be 3 to the negative second power. Please pause this video and try this one on your own. Now, when we have a negative exponent, that means we're going to move it to the opposite side of the fraction bar. Well, there is no fraction, so we're going to assume that this is the numerator. So that means we move it to the denominator in order to make it positive, but we still need a numerator, so we put that 1 for a placeholder. Can't be 0 or else it would cancel the whole fraction out. We still know what 3 squared is, so we're going to continue on and call this 1/9. Second problem. M to the 4th power times 2m to the negative 3rd power. Please pause this video and try this on your own. Now, first we need to multiply everything together. So there's an invisible 1 in front of this m. So we're essentially doing 1 times 2, which just gets us 2. Now we have to do m to the 4th power times m to the negative 3rd power. Now remember, with one of our exponent rules, when we're multiplying and they have the same base, and in this case, they both have a base of m, you're going to take those exponents and you're going to add them together. So 4 plus negative 3 actually just gets you 1. So we have 2m, and we do have to the 1st power, but anytime something has an exponent of 1, you don't need to write it at all. Third problem. 4a, I want to add an exponent. So 4a to the third power, all raised to the second power. Pause the video and try it on your own. This exponent, because all of this is in parentheses, this exponent has to go to both parts. So we need to do 4 squared, and then we have a to the third power, which is also being raised to the second power. Now 4 squared we can further simplify because we know that that's 16. And then when we have an exponent raised to an exponent, that's when we multiply. So we're going to do 3 times 2 to get 6. And we are done. Number 4. 4a. Oh, I did it again. I'm sorry. 4a to the third power to the second power. Please pause the video and try this on your own. Now I did 3 and 4 on purpose because this is a common mistake that students make. If the 4 is not in the parentheses, it does not get that exponent of 2. So we're going to keep 4. It's not going to turn into 16. And then the a has an exponent raised to an exponent, and that's when we multiply to get 4 to the 6th power. I'm going to give you one more problem. The next problem is a challenge problem in comparison to all the other problems we have tried. But it's worth trying it on your own and seeing how you're doing. Okay, last problem. It's kind of long. Don't let it intimidate you. Just try it on your own first. So we have 4m to the 4th power. Make that look like 4. N to the 3rd power. P to the 3rd power. All divided by 8m to the 2nd power. N to the 2nd power. P to the 4th power. Okay, so I told you that this was long and don't let it scare you. Try it on your own, pause the video, just see what you get. It's also a challenge, so don't be discouraged. Okay, so we're going to lump the similar parts together. So here we have 4 divided by 8. Now, if you saw 4 divided by 8 all on its own, that wouldn't be scary at all. You would say, hey, that simplifies to 1/2. Okay, now we're going to do the same thing, but with our m's. If you saw that on its own, you would say, hey, m to the 4th power gets subtracted to the 2nd power because they both have a base of m, and we're dividing. We end up getting m to the 2nd power, so I'm going to put that on the numerator. Next, we have the n's. If you saw those by itself, you would know to subtract them from each other because they have the same base and you are dividing. So we end up getting n to the 1st power. Again, when it has a power of 1, you do not need to write that exponent of 1. And last, we have the p's. Lump those together. You do the same process, p to the 3rd power minus 4th power. You get p to the -1 power. So I'm going to write that again up here. Now we only have one more thing left to do, and it has an issue with this p to the -1 power. We want everything to have a positive exponent. So in order to make that positive, we just have to move that to the denominator. And so now I could write this 1, but I really don't need to. So I'm going to write m to the 2nd power n divided by 2p to the 1st power. But remember, when you have an exponent of 1, you don't need to write that. And this is your answer.